Hello everyone, my name is Sangyoung from Korea University in South Korea. In this presentation, I'm going to talk about intercoupled tsunami modeling through an observing generating boundary. So tsunami waves, which has typically hundreds of kilometers long wavelength, travels a very long distance. For tsunami simulations, we usually make use of a non-dispersive shallow water equation model because it is very efficient computationally and robust. But as shown in this figure here, when the tsunami waves arrive at the coast areas, you start to feel the bottom as well as being dispersed by the different wavelengths. So a shallow water equation model. So if we concern about this problem, Boussinesq model seems to be a better choice in the tsunami modeling because it can include higher order effects as well as dispersive effects. So let me briefly compare the shallow water equation model here and the Boussinesq model here based on the physical accuracy and computational performance. So if we would like to simulate the tsunami waves using the shallow water equation model like here, it will give stable and efficient results, but it will absolutely fail to catch the dispersive features in the nearshore areas around here, for example, around here. On the other hand, if we use the Boussinesq model here, it will give absolutely better result, but it is much more expensive in computations. So what if we put the Boussinesq model inside the shallow water equation model where the dispersive effects are important? By doing this, we will lose both accuracy and efficiency. So this study starts from these ideas. So in this study, we would like to couple the Boussinesq model and the shallow water equation model. To couple the shallow water equation model with the Boussinesq model, two existing models have been used. Let me explain more detail about those two models. For shallow water equation model, MOST has been adopted like here. So MOST has been developed by Dr. Titov and Noah with the support of the Professor Shinolakis at USC, and it showed various applications to tsunami events here. So the governing physics of MOST is the popular shallow water equation as shown here, which is hyperbolic quasi-linear equation. So in MOST, they have real and different eigenvalues and thus can be converted into characteristic form on the right hand side here. So these equations straightforwardly describe that characteristic variables propagate at characteristic speeds without changing their quantities, which is called Riemann invariant. To solve shallow water equation in MOST, an explicit finite difference method with the first order accuracy in time and the second order accuracy in space had been adopted. This discretized equation shown here shows how the model calculates its variable and new time step numerically. Moreover, multiple nested grid system can be employed to obtain enough resolution at target area. Then let me explain about Boussinesq model that I used. For the coupling, a depth integrated model for weakly dispersive, turbulent, and rotational flow fluids. So next, let me explain about Boussinesq model that I used. For coupling, a depth integrated model for weakly dispersive, turbulent, and rotational fluid flows has been adopted. This model includes the effects of bottom-induced turbulence as a second-order correction terms to the conventional type of the Boussinesq model. It has been applied to many historical tsunami events as shown in the slide, such as the 2004 Indian Ocean tsunami and 2011 Tohoku-Oki tsunami. So this slide shows the given equations in the Boussinesq model. These equations are derived from Navier-Stokes equations, not from the Euler equations or potential theory, in order to consider higher order turbulent effects or flows. These equations look like quite similar with conventional Boussinesq model, but it has additional terms to represent bottom-induced rotational and turbulent effects of higher orders. So these red box terms are those new terms. To solve these equations, the finite volume method had been applied. For leading order terms, I mean the shallow water equation terms, fourth order multiplicativity scheme had been applied, incorporated with approximated HLL Riemann solver. For higher order terms, on the other hand, cell-centered finite volume method had been also applied. And for the time integration, third order predictor and fourth order corrector scheme had been adopted. Then a simple one-way coupling will be developed to combine MOST and Boussinesq model, as the MOST version 4 communicates between its layers. So we can just put the Boussinesq model inside any layers in the MOST model through the observing generating boundary conditions. From the standpoint of computational efficiency, it is postulated that we can get advantageous flexibility features imparted by coupling approach using generated observing boundary. So let me explain about observing generating boundary condition. For the Boussinesq model to be nested into MOST with characteristic governing system and to get variable without any errors. Non-characteristic Boussinesq model requires special treatment at the boundary. Observing generating boundary condition developed by Van Dongeren and Svensson is utilized with a special care on primary variables in the Boussinesq model. However, Boussinesq model includes higher order terms which may result in spurious errors when used characteristic boundary conditions. Therefore, the higher order dispersive terms in the Boussinesq model will be neglected near the boundary. So we're gonna put some like the bumping zone near the boundary. So we have modified Boussinesq model to get the characteristic information at the boundary without any errors. We tested the modified model in order to check whether the condition can be provided well through the observing generating boundary. The movie on the left shows one sine wave reflecting from the wall on the right-hand side. So the wave had been reflected on the wall on the right-hand side here. And we can notice that there is no significant errors at the boundary. So this is the similar one with this one, but it is like the oblique incident wave at this boundary and this boundary as well. So we can see that we have successfully generated the monochromatic waves without any errors. Then we move to more realistic case. So we tested the observing generating boundary for random wave propagating over real bathymetry, as shown here. So in this case, we used sponge layers on east here and the west side here, while observing generating boundary conditions at the southern boundary here. So the irregular wave had been generated at the bottom of the domain here, and some waves had been observed through the sponge layers on each side here and here. So we can notice reflected wave at the shoreline here are going to out through the bottom boundary without any errors. So all the reflected waves have been successfully going through this observing generating boundary here. And finally, as a practical test, the coupled model was applied to the historical tsunami event 2011 Tohoku-Oki Japan Tsunami. We deployed totally 5 layers in the ocean with different size and resolutions. The first layer covers the entire range of the domain, including tsunami generation and propagation. And smaller areas but finer grades is placed inside the first layer, and again we did the same thing for the another sub layers inside the second layer and third layer and so on. So this procedure repeated until we get the final resolution at the area of our interest. The final smallest domain but with the finest resolution is then solved by the Boussinesq model. So this animation shows the free surface elevation at the final layer calculated by the Boussinesq model. And we measured the free surface elevations at the gauge locations. And we compared that with the measured data. And this plot on the right-hand side shows the result. And we can notice that the modeled results seem to be in a good agreement with the measured results. So here are final conclusions. In this study, the MOST and Boussinesq models are coupled through observing and generating boundaries. Numerical tests have been performed to validate the coupled model, and the result shows seamless connection through observing generating boundary between two models. Developed intercoupled tsunami model provide advantageous flexibility through the spot focusing application of Boussinesq model of the entire domain of the tsunami simulation. And any add-on model to the Boussinesq model will make the intercoupled model more brilliant for general applications such as the sedimentation by tsunami waves or oil spill by tsunami waves. So this is the end of my presentation, and thank you for all of your attention. So here are the final conclusions. In this study, MOST and Boussinesq model are coupled through the observing and generating boundaries. Numerical tests have been performed to validate the coupled model, and the result shows the seamless connection through the observing generating boundaries between two models. Developed intercoupled tsunami models provide advantageous flexibility through the spot focusing application of the Boussinesq model of the entire domain of the tsunami simulation. Any add-on model to the Boussinesq model will make the intercoupled model more brilliant for general application. For example, sedimentation by tsunami waves or the oil spill modeling by the tsunami waves. So this is the end of my presentation. Thank you for your attention.